Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Chance Millett-Bangs from the Business Review, and I will be your host. It is our pleasure to have NEC Energy Solutions with us today, who will be discussing making the shift to lithium-ion batteries. Today's guest speakers are Greg Guerra, Senior Systems Engineer of Applications Engineering, and Robert Gon, Director of Product Management. I'd like to welcome you to our webinar platform on 24. This webinar is browser-based, so if you disconnect, please click the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the Q&A widget at the bottom of your screen, or use the questions box at the top left-hand corner of your screen. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. Please use the help widget if you require any more assistance. So, without further ado, please allow me to welcome Bob. Bob, over to you.
Thanks so much, Chance, and allow me to add my welcome to all you who joined this. Good morning or good afternoon or good evening, depending on where around the world you might happen to be at this moment. Our goal today, and just a brief look at agenda and goals, is to try to explore and look at the key differences between lithium-ion batteries and lead-acid batteries in particular, which are the leading technology used today in the type of markets and applications that we'll be discussing. One of the ways we're going to do this is look at the different criteria for evaluating how you might choose a battery in the types of industrial applications we're looking at. And then we'll examine some use cases, and Greg will lead us through that, illustrating how these evaluation criteria might be applied to a few example applications. And then we'll open up for some time for some Q&A. So let me dive right in. The overall global battery market is a very large place, as we know. So many devices. In fact, at this moment, any one of us probably has two different battery-operated devices on our person at this very moment. And we want to focus in and just to really make sure we understand the type of applications that we're looking at as we talk about in this webinar. We're not talking about consumer and portable devices or transportation batteries that might be in electric vehicles. We're looking at the industrial segment where 12-volt lead-acid batteries are the dominant technology today. Within that industrial segment, we are not necessarily going to be talking about the grid space. Now, the grid space is one where NEC Energy Solutions is probably best known. We've got, well over 100 megawatts of very big and very complex batteries based on lithium-ion technology deployed around the world. But what we're going to be focusing on today is looking at the applications associated with the stationary, non-grid type space and some applications in the motive space that are part of the overall $15 billion industrial battery market. So just to clarify the types of applications we're talking about. Now, when we look at different technologies that might be applied to these industrial batteries, we're looking at the typically lead-acid, different types of nickel technologies, and then lithium-ion technologies. And this chart on this slide here kind of illustrates why lithium-ion has, over the years, and continues to gain lots of attention. If we look at the efficiency of these batteries in terms of the amount of energy that is provided per unit of space, watt hours per liter, or per unit of weight, this is watt hours per kilogram, you can see that lithium-ion promises the opportunity to provide much, much greater energy density, or specific gravity, as it's called, than the other technologies, particularly lead-acid, which is the dominant technology today for many of these applications. So it's a promising technology and provides a lot of interesting benefits. But it's not just the density of the energy, but how that energy can be used. And we're going to explore that a bit in this webinar. So just as a brief refresher, or at least an overview, for those who may not be terribly familiar with battery technologies, the way a lead-acid battery typically works is it's made up of individual cells that have lead plates of some type, usually some sort of combination and treated piece of lead, in some sort of electrolyte, some sort of a sulfuric acid type solution. And the chemical reaction between these elements is what allows the battery to store electrical charge and discharge. And these batteries are combined in series to create the different voltage that would occur on that battery, and typically for the types of batteries we're talking about here, it'd be 6 of these cells combined together in series to form a 12-volt battery. Now, there's many, many different types of lead acid. They've been around for 100+ years, and they've been incremental advances over that time. So the big batteries that we may all be used to in larger installations, and even in the old days of our automobile, would be the flooded, liquid type electrolyte, which has certain characteristics, but one of those is that you have to maintain them, maintain the water, and avoid any kind of spillage that might be associated with them. The more popular batteries today, particularly in the applications that we're exploring today, are sealed lead acid batteries that use a valve, or sometimes called a valve-regulated lead acid battery. That is a sealed battery that uses some sort of gel or absorbed glass mat as the electrolyte material so they don't spill, non-spillable batteries. There's some trade-off in performance to do that, but there's a wide range of different batteries available in this. And then there's a new breed of batteries that often termed advanced lead acid that use different types of advancements in the type of lead that's being used or the plating to get some incremental improvements over the traditional lead acid. So this is just an overview of what's out there, and there's plenty of different technologies and product lines from various lead acid manufacturers that promise different types of capabilities for each one of those areas that are optimized. Lithium-ion battery works a little bit differently. It still has an anode and cathode, similar to the plates that would be in a lead acid battery, but they can be formed into different shapes, typically what we call a cylindrical cell or a prismatic cell, and it's the action of lithium ions between the cathode material and the anode material that allows the battery to store energy, usually at a considerably higher density than other technologies. Like lead acid, there are different types of lithium-ion batteries, different what they call chemistries. Lithium iron phosphate or lithium cobalt oxide, or probably a dozen other different combinations, each with slightly different characteristics associated with that. And then there's a battery management system typically associated with a lithium-ion battery that monitors, balances, protects those cells from abuse, which we'll explore in a minute why that's important. So, and really the key issue here around the battery management system is, protecting the battery from safety concerns. Now, anyone who's been, knows anything about batteries or looking in the news, has some experience understanding that there's been some concerns around safety. Now, before I say that, you realize that there's lithium-ion batteries all around us. In the cell phones we might be holding in our hand right now, and the laptop we might be watching this webinar on are lithium-ion batteries. They're all around us. They range in very small size that's associated with portable devices up through the very, very large-scale, megawatt-scale batteries that we provide to grid customers. But there have been some incidents around some of these lithium-ion batteries where they overheat due to some sort of fault in how they're managed or fault in construction of the cell. And these have been high-profile ones, the most recent one being the fires that were on the Boeing 787 Dreamliner that grounded the fleet about this time last year. The fact is that because lithium-type-based batteries provide a very, very high energy density, they also provide a higher risk of some sort of thermal runaway if they're abused. And if they do burn, it's a fairly serious issue. So the real key here is, battery design for lithium-ion must prevent and limit the effects of any of these abuse to prevent the kind of abuse or defects from occurring, and find ways to contain those situations if something does go wrong. So the approach to battery safety for lithium-ion is to really look at it a multi-layer way. At the first level, at the battery level, and a battery is a combination of different cells, the battery management system and then internal construction techniques really have to guard against putting any cell into any kind of serious condition that would cause it to fail in a bad way. And those are preventing things like overcharging, over-discharging, any kind of overheating event, or preventing short circuits on the terminals. So these are all the kinds of things, and there's a lot of subtlety about how this might be done very effectively in a safe way. But it's the basic role at the battery level. Beyond that, at a system level, where multiple batteries may be connected together, there are different protections and capabilities that have to be comprehended in the battery as well for how these batteries link together and how they work in strings and in overall power system operation. And then last and certainly not least is any type of cell design in the actual chemistry used. Different chemistries have different levels of, I guess, safety in the case that they are abused. LFP, the lithium iron phosphate, tends to be inherently safer and more abuse tolerant than other technologies, but really it's about creating a system and an environment for the battery where the cells are not going to get in an abuse situation and cause any kind of issue. Now, in addition to battery manufacturers learning about this and doing a good job, or should be doing a good job, of preventing these situations, safety and testing agencies have focused on this, and there are a pretty myriad set of standards that any quality lithium-ion battery has to go through. This is really a sampling of the types of standards and testing protocols that go on today, both at the cell level with the UL 1642 and then IEC 62133 and UL 1973 at the overall battery level. And then as a subset, or at least a linkage from the UL 1973 to UL 991, is kind of a new piece of standards that are being applied to lithium-ion batteries, particularly those who are using any kind of solid-state controls for safety. And you can see here that there's a pretty wide set of additional tests, including fault tolerance tests, that a quality lithium-ion battery should be putting itself through. So the bottom line here is that with the various standards and testing techniques and high-quality design and implementation, there's no reason a lithium-ion battery should be any less safe than any other battery out there. And I'll also just point out that lead-acid batteries aren't necessarily perfectly safe either. There's been spills and other issues associated with those, as well as venting of gases and different types of batteries. So while there's a different type of system, every battery has to be handled with some care. So let's pause for a moment and take a look at how we might evaluate different battery technologies. What are the things that are most important as we try to use these batteries and the kinds of industrial designs that we're talking about? The first one would be performance. And under performance, I'm looking at two different things: the actual energy capacity of the battery and how power is delivered out of the battery, and then how we might charge the battery, since the use of a battery really is all about charging it up and discharging it when we need it. The other factor, well, the performance factors are really about whether the battery meets the need of the application. The other factor is how long will that battery last within that application, something we call the service life. And there's two pieces of that we'll explore. The third criteria would be how does that battery perform over different types of environmental temperatures. Historically, batteries have been very temperamental about how they operate at room temperature versus at higher temperatures or lower temperatures that might be part of the industrial environment. And then, as we alluded to in that early slide, the weight and energy density, both per unit space and per unit weight, is another key criteria. And then how we might maintain and manage those batteries is something to look at. And then, of course, nothing is complete without looking at the costs associated with that. So let's take a brief tour through each of these criteria, looking at what it means to system design and how lithium-ion and typical lead-acid batteries compare. So before we do that, we need to define a few terms to make sure everyone's kind of on the same page when we talk about certain attributes. The first is we talk about capacity. Capacity is really kind of the fuel gauge, or at least it's basically talk about the size of the battery. And that's measured in amp hours, basically how much current can be delivered in a certain unit of time. And it's basically the available amp hours when the battery is discharged from 100% state of charge or 100% full down to being empty. Energy of the battery is really the same measure, but it's really the measure of power, watt hours. So it's a combination of the amps times the voltage changes as it's being discharged. And again, from 100% full or 100% state of charge down to zero or an empty charge, which is defined by the cutoff voltage. The power that the battery is capable of delivering is the instantaneous energy flow, or the rate at which energy is transferred from the battery, measured in watts. And then voltage, hopefully, is fairly obvious to us who are interested in batteries. And then a concept to understand is called C rate, which is a measure of the rate at which a battery is discharged or charged relative to its maximum stated capacity. And this is a way for us to use the language of what the battery is capable of, independent of the size of that battery. A 1C rate means a current that discharges the entire battery in 1 hour. So it's a combination of the rate and the time. A 2C rate would be a current that discharges the battery in half an hour. And a C over 2, or 0.5C rate, is a current that discharges the entire battery in 2 hours. So a C over 2 would be a 2-hour duration. A 1C rate would be a 1-hour duration. And a 2C rate would be a half-hour duration, and so forth. So let's look at the first criteria for evaluation, which would be for battery performance, which would be capacity. And the thing to look at here is how capacity varies with the power level, or the power rate, at which we're using the battery. And this may not be something that everyone understands completely. It turns out it's a well-known attribute of most batteries, in particular lead-acid batteries, is that as you take energy out of the battery at a higher rate, at higher powers, the actual capacity that's in that battery decreases. It actually decreases at a fairly rapid rate. Most lead-acid batteries are rated, when you say you have a 50 or 100 amp hour battery, they're rated at a 20-hour discharge rate, meaning that the current, the discharge of that battery, the current that's being pulled from that battery, will take all the energy out of that battery in 20 hours. So any application that you're planning on using where the battery would be covering a period of time that's less than 20 hours would actually be providing less than the rated, what we call nameplate capacity of the battery. So say you were doing a 2-hour backup scenario, which would be matching up to a C over 2 rate, a 2-hour discharge rate, if you're going to discharge the entire battery in 2 hours. The fact is that a 100 amp hour battery would really only have 75 amp hours of capacity. If you were to do a higher rate, say you wanted to discharge that, the typical, like in a UPS application, maybe in a half hour or maybe even a 60 rate, which would be a 10-minute rate, the actual capacity of that battery would be less than 50% of its rated capacity. Lithium-ion batteries, on the other hand, have a pretty much a flat discharge rate, meaning capacity versus discharge rate, meaning they can deliver the same capacity relatively independent of the actual discharge rate. So at high C rates, at high power levels, a lithium-ion battery might have twice as much usable capacity, twice as much available capacity at higher power rates than lead-acid would. And this is actually a pretty important criteria for many applications that are out there. The reverse of this would be on the charging side. So there's an impact on capacity when you discharge the battery. How does that come out when you're trying to charge the battery and put energy back in? Well, most lead-acid batteries used in the markets that we're talking about in this webinar can take anywhere from 4 to as much as 20 hours to get a full charge from a completely discharged state, and actually several hours even if you're not going from a fully discharged state. This is the illustration here on this graph is assuming that the lead acid is getting charged to a full charge in 10 hours, but it could be even twice as long as that. Lithium-ion batteries charge faster, and in some cases much faster, and shown at the bottom here are 3 different versions of our ALM family, which I'll talk about a little later in this webinar, as well as another lithium-ion vendor who, again, can charge much, much faster than lead acid. In these cases, we can charge at a 6C and even our little batteries as much as a 9C rate, which is much, much faster. It could be 5 to even 100 times faster than the equivalent size of lead-acid battery. And this has implications, as we'll see later, in certain applications. Now, those are just 2 of the performance criteria. The other criteria looking at different batteries is how long will that battery last in a real-world situation. And there really are 2 major factors associated with that. The first is what we call the calendar life, or which is often used synonymously, even though it's not necessarily exactly the same thing, as the float life. If a battery is being used in a pure backup situation, where it's just left on a float voltage to keep the battery topped up with charge, and it's only going to be discharged when there's some type of event that is going to be that the battery is there for, then the real life that matters is what we call the float life or calendar life. The other factor that comes into this is what we call the cycle life, and this is the number of times we can discharge the battery and charge the battery before the capacity of that battery is kind of used up, before it essentially wears out. These two things combined is what really determines the service life, and the service life is really how long that battery will last in the given application. That is some combination of calendar life and cycle life. Now, most lead-acid batteries are really optimized for one or the other application. They're either optimized for what's called float service or backup service, or they're optimized for some sort of cycling, let's say a deep cycling battery or something that's been meant to do that type of application. Trying to find something that compromises in between, tends to, there may be batteries that are compromises in between, but they usually end up not being able to do either one in a particularly good way, or at least not as good as one is optimized for the given application. A lot of data sheets for many batteries will talk about a design life or service life. These aren't necessarily super technical terms because they have to assume something about what the application is to figure out how the combination of calendar and cycle life actually provide the longevity of that battery. The other thing to note is that all batteries, independent of the technology, are affected by the operating temperature and ambient environments of the battery, and that have an effect both on the calendar life and the cycle life. So if we look at service life and compare lithium-ion versus various lead-acid, we really have to look at it and say, gee, the float life and the aging of the battery varies considerably based on, what the battery product line might be. Some actually have relatively short lifespans, as illustrated in this chart. It can be as short as 4 or 5 years before their capacity degrades to, say, an 80% level, basically meaning the capacity of the battery is 80% of what its original nameplate capacity was. And you can see that it can be pretty good for a while and then kind of falls off a cliff after time. Or it might more slowly degrade. There are certainly lead-acid batteries that are optimized for cycle life that can be in a float application and lasting up to 15 years, some up to 12 years as illustrated here. On the other hand, the lithium-ion offers some improvements in float life compared to even the best-in-class backup-type lead-acid battery in having a float life that would exceed past 15 years. There are certainly other things that might cause that battery to wear out before the actual float service life would be. This allows the lithium-ion battery to provide more capability for a longer period than most lead acids, even those that are optimized for the float life. The other aspect of service life is in cycling applications. And this is the area where the lithium-ion, as a general technology, has really shined compared to lead acid. This is the reason why it's in our cell phones. This is the reason why it's in our laptops. This chart is an illustration of actual test results from the cell technology that we happen to use in our ALM lithium-ion product line. In fact, it's the same technology used in our grid storage systems. And this is demonstrating a cycle life, even at a relatively high charge and discharge rate, that can exceed 8,000 cycles to 80% of the beginning of life capacity. So when the capacity drops to 80% of its beginning of life, we're at 8,000 cycles. We actually can continue onward to many, many more cycles down to approximately 60% beginning of life and go as high as 20,000 cycles. Not all lithium-ion batteries can go that far, but most lithium-ion batteries can go far further than lead-acid batteries. The other factor here is that cycle life is really dependent and affected by how deep you would discharge the battery for each cycle. So, and also, the rate at which you charge and discharge. The deeper you go, or the faster you charge and discharge, the more quickly the battery will wear out, especially for lead acid. So in this example, I'm comparing, it's not really a fair comparison between these various devices. The two charts we're showing for the cells that we use in our particular batteries are using a 1C, 1C, basically charging it for an hour, discharging for over an hour, and completely discharging the battery 100%. Whereas the lead acid battery here in the red line here, I'm only showing that for a 30% depth of discharge and charging only once per day, up and down, as opposed to once per hour. Even at 100%, the cycle life, even at the lower discharge rate, is something less than 200 cycles versus the 8,000 or more for lithium-ion. So in one sense, this comparison chart here is overstating the capability for the lead acid, but you can see the big difference here and why lithium has been has really been accepted in the market in many different applications because of its long cycle life. So let's take a look at the effect of temperature in battery performance, the other criteria. The red line here, and I'm sorry if this chart's a little bit difficult to read, the red line here shows the performance and the usable energy or capacity of a lead acid battery versus cold temperatures below room temperature. So you can see that as we get lower temperatures from room temperature of say 25 degrees Celsius down to minus 30 Celsius, as it might be typical of an outdoor application, the actual usable capacity drops down to just north of 40%. So if you're going to use a lead acid battery and not provide any kind of heating associated with that battery, you're going to have to oversize your system and plan for only less than 50% of that capacity, even not including the capacity issues associated with the discharge rate that we talked about earlier. It's going to drop, you have to basically plan for more than 50% of that capacity to be gone, to not be available to you. Now, with lithium-ion, it also drops versus temperature, but not nearly at the same rate. In a situation, the blue line is the lithium-ion, as an example for our particular ALM battery. And even here, we're showing that our result at a much more challenging discharge rate of C over 2 versus the C over 20 discharge rate for the lead acid. But even here, our capacity at that minus 30 degrees centigrade only drops to about 75% of the original capacity. So we're still reduced, but not nearly as much as a lead acid. At higher temperatures, the capacity actually does pretty well for both technologies, but the float life and to some extent the cycle life of both technologies is significantly reduced. So at lower temperatures, you lose capacity. At higher temperatures, you lose life, and that's how temperature affects these batteries. So what this all boils down to is how do we understand what the usable capacity of the different battery technologies are? The usable capacity is really what you have to design to when you're using these batteries in a system. If you need to back up energy for 2 hours under certain conditions, then you have to derate the different batteries based on how the different factors affect that. So here's a chart that kind of takes this kind of highlights the significant differences between lead and lithium-ion for, I think, a relatively straightforward application. The target application would be 2 hours of backup, have to work over 10 years, so there's some degradation associated with the float life over that 10-year period. Over that 10 years, we're probably going to have some instances of use for this. So say we're going to cycle the battery 500 times over 10 years, which is not a whole lot, and we're able to maintain that battery, say, at 25 degrees C. In this instance, as we derate the capacity of that lead acid battery, and in all these comparisons, I'm trying to use a high-quality lead acid battery that's optimized for that given application. You might see that only 30% of the stated nameplate capacity of that battery is actually usable once you derate those factors. And one of those things, and the red factor there, is being able to limit the depth of discharge for those cycles. So say in this case, limiting it to 70% depth of discharge in order to get to those 500 cycles over that 10-year period. Lithium-ion, on the other hand, could go to 100% depth of discharge, and the only derating that's really necessary is that little bit for float life after the 10 years, what the capacity loss over a 10-year period would actually be in calendar life. So in this instance, lithium-ion has up to 3 times the actual usable capacity of a lead-acid battery, which means a 30 or 35 amp-hour battery, lithium-ion, can be equivalent to a 100 amp-hour battery in this particular application on lead-acid. So that's the kind of example that we're looking at here. And the usable capacity is a big factor with these batteries. The other factor is weight and energy density. We talked about this with that graph. Briefly, this is an example where we took 3 different types of lead-acid batteries, and we kind of imagined, gee, if I have a telecom rack, half the height of a telecom rack, I populated with a bunch of batteries with as close together as I could, what kind of energy density could I get? Well, we can fit different types of batteries, different sizes. We're comparing 3 different lead-acid batteries here with our ALM 12E35 as an example of a lithium-ion battery. And it turns out that once you actually look and do a little bit of derating for the different applications and look at the number of batteries we need and what the usable energy would be within that space, a lithium-ion can provide up to 50% more usable energy in the same footprint and be half the weight of the other batteries in that environment. So we get far more energy, 3 to 5 times more energy per kilogram, and 50% more energy per that unit weight, anywhere between 35 and 50, depending on how we would configure it. So there's a lot that can be done, and this has applications in areas where weight and space are important. The other factor that comes in is, how do we maintain and monitor the health of the batteries in different environments, particularly when talking about industrial environments where batteries may be not easily accessible. Lead-acid batteries often require some sort of external monitoring capability to looking at what the state of charge might be and what the state of health of the battery is. Sometimes this is built into the power management systems and charging systems. They actually count how much energy comes in and out of the battery. Sometimes we look at the external voltage of the battery to kind of get some kind of guess on what the state of charge actually is. But often that's not always that accurate. There's actually a significant industry of companies, as listed and kind of shown here, some examples, who are providing monitoring systems, including sensors and communications and various analytics software, to provide some idea for battery banks and what the actual state of health and operation of those batteries are. On the other hand, lithium-ion batteries, or at least some lithium-ion batteries, actually have some of that functions built into extensions of their battery management system, and it can offer built-in monitoring and even communications built into the battery itself, so that this information can be looked at the cell level inside that battery. So just something else to consider. It's not usually high on the list or something you think about with batteries, that having a battery that might be intelligent, that can communicate this type of information and even provide some alarming associated with that. But it's something that's possible with lithium-ion batteries that is not really done with lead. And then last and certainly not least are cost considerations. And here's where the people are understanding the differences. A typical 12-volt lithium-ion battery is usually between 3 and 6 times the cost of an equivalent nameplate 12-volt lead-acid battery. And this is something that's sometimes be off-putting to people because it is a more expensive product. However, when you compare it based on the usable energy in the system, when you actually size out and derate the lead-acid battery based on its usable capacity and the environment that it will be used in, that cost difference really might be reduced to less than twice the cost. And then if you look at that in terms of the actual life cycle cost for a lithium battery over a period of years, the longer life of lithium can actually come out to be as much as 50% lower than the lead-acid battery in the overall total cost. And the chart here gives a little bit of an indication of what the initial cost of the battery is based on nameplate, dollars per watt hour. But Howard, that's not really the metric that you need to compare these against. It's really about what the cost of the overall system and the performance within that system actually is, and that's the key criteria. So now we've kind of explored these things. Let me throw this over back to Chance for a moment to poll you and see what is the criteria that's most important to your particular application. So, Chance?
Thank you very much, Bob. So as Bob has just mentioned, it's now time for our first poll question that we'll be having in today's session. This is a multiple answer poll, so please select all of the options that are relevant to you and then press submit. So this first poll question is, which evaluation criteria are most important to your battery applications? Your selection of answers are usable energy capacity, charging time and power delivery, calendar life or float life, cycle life, operation over wide temperature range, weight or energy per unit area, maintenance monitoring and management, or finally cost. So Bob, just while the audience are voting in this poll, can you just describe what kind of results you're expecting from this?
Well, it's hard to say. I mean, I haven't looked at the attendees to say what industries they might be part of. Certainly if you're designing systems that are in primarily backup environments where they're not going to be discharged very often, I would expect that the usable energy capacity and the calendar and float life would be the key criteria. However, if you're in a cycling application that is going to be constantly charging and discharging the batteries, cycle life is usually the top criteria. But some of these other ones like usable capacity and weight and so forth can be important to any criteria. So I'll be very interested to see what the results will be in this poll.
Thank you very much. That's enough time for the attendees to vote in this poll, so I'm just going to quickly move on to our results. Okay, so things seem reasonably even across the board there, but cost is our winner. Would you like to briefly discuss this before you continue with your presentation?
Well, I don't know that there's any application of any product on Earth that cost hasn't been one of the key criteria. And I'll say that's an important criteria, particularly both at a system level and at kind of a total life cycle level. So that's the key thing to be looking at. We all know that sometimes we get what we pay for on the initial product. So taking a holistic view of that, I'd say, is the thing that people should be most worried about. So having kind of looked at this, let me give everyone just a brief overview of the products that we're offering in this market, and then I'll throw it over to Greg to look at some application of these products in some use case examples that will highlight not only the capabilities of our product, but also how lithium-ion in general can compare to lead-acid in some real-world situations. The ALM product family, first off, the ALM 1235 is a 35 amp hour battery that we just announced earlier this morning. It's a family or a product line of different batteries that include what we call our standard version that is non-intelligent, and then a line of communicating batteries that provide some communications and monitoring capability. These are all very high performance, again, around the high power delivery without losing energy capacity, very fast, simple charging, and the intelligence capabilities. Very long life batteries with exceptional deep discharge and cycle life capability. And we saw an example of that in a slide earlier, where we can be over 8,000 cycles to 80% depth, beginning of life capacity, which is really the piece that differentiates us versus not only lead acid, but other lithium-ion batteries on the market. We're 2 to 3 times better than lithium-ion other competitors, and many, many times better than lead acid. These are both important for tough critical applications, and we'll explore some of that in these case studies. And we also have some very strong built-in safety characteristics, so I'll describe a little bit more detail in the following slides. First, I'd talk a little bit about the intelligence, because this is something that's a little bit different than what's out there. The I-series ALMs, those with the intelligent communications, can be integrated with system power management systems to be able to monitor and get details on what's happening inside that battery. Or they can be monitored as a separate standalone subsystem. The data that's maintained by the battery and accessible is compatible with the smart systems battery specifications, and includes some extensions to those specifications and standards for NEC batteries. We actually have an evaluation demo piece of software that's available for you to plug in and get a view of what these are. But these capabilities include, what the current and voltage of the battery is at a given moment, what its current state of charge is, voltages and temperatures at the cell level in the battery. We also provide programmable thresholds for what the remaining capacity and runtime is and charging level of the battery, and also provide some alarm and fault monitoring, so we can trigger when there's some sort of condition that might be of concern to somebody managing a battery system. In addition to the performance and so forth, is our ability to scale these batteries without having to do any external battery management system. These batteries can be configured into series configurations, so we can take a 12-volt battery, put them in series to get 24 or 36 or 48-volt configurations, and then we can scale them in parallel up to 10 batteries deep to create battery systems that can range up to 18 kilowatt hours of capacity at 48 volts. This really covers a wide range of different potential applications, and we don't require an external BMS to do this. We provide all the protection functions that are required for lithium-ion batteries in this configuration, as well as automatic balancing of capacity between the different batteries within those strings. So it's a very flexible and very easy to use battery system that's quite scalable, even though the initial capacity is 35 amp hours. And then finally, I'd like to highlight what we call our EverSafe protection technology, which is our BMS that provides the utmost level of protection and safety for lithium-ion batteries. We protect against overvoltage, over discharge and under voltage, over current and short circuit protection, over temperature, and do all the typical cell monitoring and balancing required of lithium-ion batteries. We do this with full redundancy. We have redundant sensors, redundant power electronics to provide recoverable protection against external abuse and internal faults. So not only do we protect, but we also automatically recover from most of these faults. So if that fault is cleared, the battery is not disabled, but it'll come back into use when any kind of external event that may have caused the battery to go offline to protect itself and the system goes away. So at this point, let me toss it over to Greg, who will lead us through some example use cases associated with how to use these batteries in different configurations.
Thanks, Bob. Okay, so I'm going to go over a few different applications and compare how our ALM 12V35 stacks up against different lead-acid batteries optimized for those particular applications. I'll probably go into a little more detail on the first application and maybe the second one, and then go through the last two a little more quickly so we can have time for questions at the end. Okay, so the first application is Cellular Macro Base Station. A key trend in this area is increasing site power requirements. So, a lot of batteries being added to meet the increased power requirements. Some backup power challenges in this area include regulatory pressure for longer backup times, for storm resiliency, for example. So for this reason, people are adding batteries as well. So for the increased power and for the increased energy. Broader operating temperatures due to reduce HVAC expense. So people are trying to push the envelope on the temperature range in the batteries, and if the batteries can handle it, then you don't need the HVAC infrastructure to control the temperature. Space and weight of added battery capacity, especially in urban rooftop applications. So this ties into the first two things I said. When you're adding batteries for power and for energy, with lead you might run into a lot of issues due to the weight. Buildings, a lot of times can't handle the additional weight load, and also there might not be space to put them since, because of the weight, they're typically limited to the first floor or the basement. Whereas the lithium is a lot lighter, you can put it really on any floor, or for new construction. It'll take up a lot less of your space budget, so you can do other things with that space, or, maybe due to the reduced weight, your construction costs are reduced. There's a lot of benefits there. Finally, the reliability and service life. Lead acid not quite meeting the expectations, seeing somewhere in the 3 to 5 year range versus 5 to 8 year expectations. So some typical attributes of these applications: 1.5 to 3 kilowatts of power, around 4 to 8 hours runtime. And one important thing is stable grid for these applications, fewer than 10 to 20 hours of runtime a year. So as Bob mentioned earlier, the kind of two components to the service life would be the float life and the cycle life. So for this particular application, you're more concerned with the float life due to the low cycle count. Also, environmental diversity with these, so you want to be able to withstand wider temperature ranges. So just going to take a closer look into some of the numbers. For this configuration, we chose 1.5 kilowatts, 12 kilowatt hour. So that's an 8-hour runtime. We're looking at minus 30 degrees C to positive 35 degrees C. And again, that having the battery being able to handle that temperature range, allows you to reduce your HVAC expenses. And we're comparing a quality sealed lead acid battery versus our ALM 12V35 over a 10-year period. So just taking a quick look at the table here, you can see the nameplate capacity is comparable, 35 amp hour for the ALM, 40 amp hour for the lead. But once you get into those deratings that Bob mentioned, for the temperature, for instance, we're derating 30% compared to 50% for the lead. And also, we allow 100% depth of discharge as opposed to 80 for the lead. So once you take those into account, even though the lead has a slightly higher capacity, you still need quite a few more of these lead batteries to get the equivalent configuration of lithium. 64 as compared to the 36 for lithium. And due to that oversizing, you get the pretty big weight difference, 227 kilograms versus 813 for the lead. The usable energy ends up about the same, which is the whole point of the exercise, oversizing the lead, which you have to do to support the application. So with this, the upfront cost is a little bit more for the lithium, no surprise, about 70% higher. And then that last piece of the puzzle of cost is the service life. So getting 10 years with lithium as opposed to 5 with the lead acid, that really swings the cost in favor of the lithium. So for this case, we end up with 70% less weight, 40% less space, twice the float service life. The cost ends up similar, but the lead is slightly higher. And there are significant operating cost savings, which were actually not factored in to this bar graph that you see here. Okay, so the next application, weak or off-grid base station. A key trend there, obviously, is we're seeing growth in markets where grid is unreliable or absent, hence the weak or off-grid. Growing interest in green power to reduce or eliminate gensets. And the reason for that is, the first challenge there, genset fuel and delivery is the largest operating expense. Another challenge is the lead acid batteries can't accept those high charge currents, where the diesel gensets are most efficient. And the lithium really can make a difference here. For example, in an off-grid situation, when you're recharging the batteries, the genset also would have to drive the load. which is not constant. In those instances where the load might be lower, the genset is not operating at its peak efficiency. Whereas with the lithium, you can actually control it such that when the load is lower, you just charge the battery faster. You take that additional power and you give it to the battery. So that does two things. It charges the battery faster, so you're not running the genset as long, and also the genset is running at peak efficiency for the whole time. So that's certainly advantageous. PV-based systems may drive battery operation at partial state of charge. Obviously, you can't count on the sun being there 100% of the time, so that's unavoidable, and the lithium being able to tolerate that is certainly an advantage. And again, obviously, service life is key. And lastly, theft is actually a concern in some of these remote locations, the fuel and equipment. So I'll just skip right to some of the numbers here. So for this example, 1.5 kilowatt, 6 kilowatt hour. So that gives us a 4-hour runtime. We're controlling the temperature, so between 20 and 25 degrees C. Comparing a quality partial state of charge optimized SLA battery versus our ALM 12V35, again over a 10-year period. So I won't spend as much time on these numbers, but 35 amp hour lithium battery again, and now compared to an 82 amp hour lead acid battery. So it's a bigger battery, but due to the allowed depth of discharge, you still need more of them. So 16 ALMs versus 24 lead acid batteries. So again, you're talking about a lot more weight, around the same usable energy. For this, the initial cost is actually pretty close. And then, like Bob said, once you get into the service life, it really swings it in favor of the lithium as far as cost is concerned. And so another key thing with this one, which isn't quantified in the cost savings, the 2 to 5 times faster charging time, and there can certainly be some cost savings associated with that as well. That really depends on the specifics of the application. So the third application, industrial UPS. A typical attribute, very high power, between 5 and 15-minute discharge times, remote, environmentally harsh. So for this example, we went with 500 watts for 12 minutes. So that's actually a 5C discharge rate, which is very, very high, certainly for lead. It's within the range for lithium, but still on the high end of that. 0 to 50 degrees C, and rather than kind of scaling the lead, oversizing to meet the power and energy requirements, for this example, we're sticking with the 3 batteries in this form factor of the 2U rack mount UPS. So you can see, the usable energy for the lithium, 162 watt hour versus 86 for the lead. And again, partly because we didn't oversize the lead for this example. You see a little bit bigger difference in the upfront cost, still about 5 times more expensive. But then again, you look at that service life, we're about 5 times longer there. So it does bring the cost down to the same area as the lead acid solution. So you can see the usable energy by 62%, whereas the lead falls short by 14, 65% lighter, which is pretty much always going to be the case, and like I said, a little bit more expensive for this particular application. Okay, so the last one, off-grid power systems. And there are broad applications really for this type of situation. You see lots of LED lighting, SCADA, signage, remote communications, etc. And a lot of these are PV powered, and some diesel gensets, most of them outdoor environments. For this example, we chose 500 watts, 3 kilowatt hour, so you have a 6-hour runtime. And again, wide temperature range, 0 to 50 degrees C. comparing that same quality partial state of charge optimized SLA battery versus our ALM 12V35. And you can see the numbers in the table on the left. I won't go through them all again. But for this situation, the lithium solution, less than 1/3 the 5-year cost, 1/8 the weight, obviously less space too, and again, faster charging, which can help you out in reduced fuel costs. So that's it for the use cases. So I'm going to hand it back over to Chance for our second poll question.
Okay, Chance, are you there?
Sorry about that, I left myself on mute. So again, this is a multiple answer question, so please select all of the options that are relevant to you and then press submit. So this second question is, which battery application areas are you most focused on? Your answers are wireless communications, wireline communications, UPS systems, medical equipment or computer carts, off-grid power systems, residential solar PV and energy storage systems, mobility for the disabled, or finally other. So Greg, just briefly while the audience are voting once again, can you just state where is the lithium-ion gaining the greatest traction?
Well, we are seeing probably the greatest traction in the medical equipment space, also the wireline and wireless communications, especially outside the U.S. But really, there's such a broad range of applications that lithium would be good for. So I wouldn't be surprised to see other, or any one of the other answers as well.
Thank you very much for that. I believe that's enough time for the audience to have voted, so let's quickly move on to our results. Okay, so again, it's a reasonably even split there, but UPS Systems is our current sort of winner. Would you like to briefly discuss this before we move on to our Q&A session?
Yeah, well, like I said, no real surprise. That's certainly a space where lithium can bring a lot to the table. So really not surprised at the answer, I guess. So yeah.
Excellent, thank you very much. So we'll now quickly start our Q&A session. We've already had a lot of questions in, but if you do have any more, then please submit them using the questions box or the Q&A widget. So moving on to our questions. Our first question is the ALM 12V available now?
And the answer is yes. 12V35 product is available as of, well, we announced it this morning. It's in production availability and being manufactured in volume. We also have a 12V7 that's been available for some time, and a new generation of that will be available in the coming weeks as well. So the answer is yes.
Thank you very much for that response. Swiftly moving on, our next question is, any flammable off-gassing?
And the answer to that is no. Unlike some of the lead-acid batteries that, particularly when they're being stressed at high charging and discharging rates, can off-gas dangerous gases and release them, particularly the flooded batteries, to the extent that for large installations they really need to be kept in separated battery rooms for safety's sake. There is no flammable off-gassing. So this allows the lithium-ion batteries to actually be used in some environments where lead-acid might be inappropriate, or special containers might be required to vent the battery room to prevent any buildup of such gases.
Thank you very much for that. Unfortunately, we've running out of time here, so our next question is going to be our last question of the session. However, any questions that we haven't got to answer so far will be forwarded to our speakers along with your email address, so you will receive a response in due course. So our final question is, most batteries have special specifications for float life and for cycle life, but how do these combine for overall service life in mixed applications?
Well, this, and Greg knows this better than anyone, This is one of the toughest questions that we have, particularly when you look at the lead acid data sheets, because they don't provide the kinds of combination question answers, much less even detailed answers around cycle life, such as what charge and discharge rates are their cycle life charts given for, and other assumptions. It is a complicated question. It requires some analysis for a given application. It is something that there's a particularly challenging application, something you can contact us with, and we can provide you some good guidance. But what I can say is that, and we actually have an example chart of some of these analyses in our data sheet that you can find on our website. But we can have a total service life. Even if you're discharging 100% depth of discharge 3 times a day, we can have a combined calendar and cycle life, or combined service life, that exceeds 10 years. So this is one of the real powers of lithium-ion in general, and more specifically of the ALM product family.
Thank you very much for that. Just before I conclude, I'd like to inform the audience that a copy of today's presentation will be available for you to download from the green resource list widget in the on-demand version of today's webinar. Before I conclude, do either of our speakers have any final thoughts that they wish to leave with the audience?
Well, I guess one thing that we both definitely mentioned that I would like to just kind of mention as a key takeaway is really the usable energy. You really need to understand how to make a fair comparison there. It starts with a derating due to discharge rate, derating due to temperature, allowable depth of discharge, and that gets you your apples to apples cost on day one. And then after that, it's the service life, which really gets you your total cost of ownership. So that's you need to have that kind of calculation in mind when you really choose your system.
Okay. And all I'll say is that I want to thank everyone for attending the webinar today. And if you're interested in looking at some more information, we have that available on our website. As of this morning, we announced the product. And I'd also look forward to more information from us as we roll out various applications of these products and provide more details on how they can be used and the specific applications that are deeper examples of some of the case studies we demonstrated today.
So that just leaves me to thank Greg and Bob for what was a great presentation, and thanks to NEC Energy Solutions for sponsoring today's session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.